So good afternoon. My name is Michel Baudouin-Lafont. I'm a professor in computer science at the University of Paris Sud, near Paris. I'm also a member of the ACM Europe Council. And in this capacity, I was asked by Wendy Hall and John White, the ACM President and the ACM CEO, to welcome you here and to introduce the Turing Lecture. So it's a great pleasure for me to be here, a great honor as well, to welcome you to this ACM A.M. Turing Lecture. This annual presentation is given by the winner of the ACM Turing Award, named for British mathematician Alan M. Turing. This honor is often referred to as the Nobel Prize of Computing. It is the most prestigious award a computer scientist can receive, and it carries with it a $250,000 prize, generously provided by Intel and Google. The winner of this award may choose the conference site of his choice for the Turing Lecture. And happily for us, he has chosen the 37th International Symposium on Computer Architecture, ISCA, here in Saint-Malo, France. It is quite fitting that his presentation will take place in Europe. The ACM community here is vital and is growing. It now numbers more than 15,000 members, and as a result, ACM has increased its support for their activities. Not only in Europe, but all over the world. This year, for example, it launched the ACM Europe Council to raise the level of ACM participation and visibility on the continent. Recently, in India, it established the ACM India Council, and the organization is also increasing its presence in China. So all of these efforts are testimony to ACM's commitment to its mission to advance computing as a science and as a profession. In that regard, it is highly appropriate tonight that we hear from an individual who has truly advanced our profession. Too often, we use the term pioneer a bit lightly when summing up a career. Well, let me tell you, not in this case. The term pioneer truly applies to Charles P. Thacker, also known as Chuck Thacker. In fact, no other word will do when one examines his accomplishments as the architect, the inventor, the designer, and the builder of so many of today's personal computing and network technologies. Chuck was educated in physics at Berkeley in the 60s. He joined Project Genie in '68, which was a project building an early time-sharing system. This project turned into a company, the Berkeley Computer Corporation, BCC. Shortly after, in 1970, he joined the Xerox Alto Research Center, PARC. And in the 90s and 80s, he was a central systems designer and the main engineering force behind many of PARC technologies. Among them was the Alto, the first modern personal computer with a bitmapped screen to run a graphical user interface. Chuck Thacker gave new meaning to the concept, what you see is what you get, and every PC today is a direct descendant of the Alto. Let me give you a short personal story about this. It's not really about the Alto, it's about the commercial offspring of the Alto, the Xerox Star. My area of research is human-computer interactions, quite far afield from computer architecture, but precisely in the work of Chuck Thacker, this has been together in many of his projects. In the late 90s, a small group of people managed to put together a Star machine and make it run. And they ran the last Xerox Star demo, and then another one, and then another last Xerox Star demo. And I was lucky enough to attend one of these live demos at the CHI conference. And for me, it was really defining moments in my career. I realized how the tight integration of hardware, software, and user interaction was really the ground for a new revolution in computing. But of course, this wouldn't have happened without Chuck's work on the Alto. His accomplishments, however, do not end there. He went on to invent the snooping cache coherence protocols used in nearly all small-scale shared memory multiprocessors. He also pioneered the design of high-performance, high-availability packet local area networks, the Ethernet. He designed the Firefly at DEC, which he joined in '83 as a founding member of the DEC CERC laboratory. The Firefly was the first multiprocessor workstation. He also worked on the Alpha demonstration unit. I actually also had the opportunity to work on these workstations, and it was truly amazing to see the future in front of ourselves. 3 decades after the Alto, after he joined Microsoft Research in '97 to help establish the Cambridge lab, he also designed and built the prototype for the most widely used tablet PCs today. A pioneer, an innovator, a visionary. Absolutely the right words. The subject of his talk this evening is improving the future by examining the past. Ladies and gentlemen, mesdames et messieurs, dear friends, please welcome the winner of this year's ACM A.M. Turing Award, a technical fellow from Microsoft Research, Chuck Thacker.
Well, thank you very much. Tonight I'd like to thank the ACM and the nominating committee and the sponsors of this award, Google and Intel. And I'd like to particularly extend my personal thanks to Intel for their strong support of activities like the International Science Talent Search, which try to increase the interest of young people in science. I think this is a very great thing they have done. This is definitely an award that I never expected to win, because it's actually been 43 years since the Association for Computing Machinery gave this award to someone whose primary contribution has in fact been computing machinery. A lot of other people have gotten the award and they've all done good things, but they have not been machinists. I'd also like to, can we key up the slides, please? Thank you. I'd like to make particular note of some collaborators of long standing. These are people with whom I have worked in the 3 laboratories that I have worked over most of my professional career. The most important of that person up there is Butler Lamson. The thing that wasn't mentioned and is frequently forgotten is that I do not have a PhD. I am not Dr. Thacker, except for an honorary degree. But I can tell you that working with Butler Lamson for approximately 2 years is the equivalent of about 5 PhDs. This choice of people with whom I have collaborated generally reflects the view that I've had about picking my collaborators, and it's something that I advise new people in the field to do as much as they can, which is choose people that are smarter than you, because you learn so much from them that it's just it makes your life a pleasure, and working with Butler has done that. Butler and I worked together on, not so much on the 940 system, which I was employed by the university to help build, but on the follow-on Berkeley Computer 500, the MAX time-sharing system, the multiple access Xerox computer, which is a fairly large PDP-10 clone, which we had to build rather than buy because Xerox had just bought a computer company. They wanted us to use their computers, but we thought they weren't satisfactory because the ARPA community, the ARPA research community all used PDP-10s, so we built one. Worked out pretty well. And then finally, we understood what we should have been doing, and we built the Alto. We subsequently built a couple of other machines, the Dorado, the Firefly, and a couple of networks, the AN1 and AN2, and finally the tablet PC. Butler and I worked together on all those projects. A few other people, Ed McWright, who's perhaps better known as the inventor of the D-tree, worked with me on the Alto hardware, designing the disk controller. Mike Schroeder came to us from MIT at PARC, and we've worked together more or less ever since, with a brief hiatus after he elected to stay at DEC when I had seen the handwriting on the wall and went to Microsoft. So we worked on the Firefly, the AN1, the AN2. Roy Levin, who's now the director of the laboratory in which I go to work every day, Mike is the associate director, and I have worked on the Firefly. Andrew Burrell is also a long-term collaborator with whom I work today on a thing called Beehive, which I'll tell you a little more about later. And of course, there have been dozens more people. An award like this is not given to an individual. It's really given to a team. And I've had a lot of teams, and I like to think of myself as a good team leader, but not a good manager. So I've enjoyed working with all the people with whom I have worked, and I hope that they have enjoyed working with me as much as I've enjoyed working with them. So most Turing lectures actually are, and I've studied quite a few of them over the last few months, are either career recapitulations, that is, I tell you what I did, or they are, in fact, grand challenges for the future. And I decided that I would try to do something different. I have a thesis, which I will propose, and I will provide some examples to try to defend that thesis, and we'll see how that goes. Now we have to figure out how to advance the projector. There we go, almost. Now we have to figure out how to get that thing out of the way. That seems to work. So the thesis is fundamentally that computer architecture has hit a wall. I'd like to apologize, by the way, to the ISCA crowd here, because what I'm going to say is something that you folks know very well, and I'm sorry, but you'll just have to bear with me because this talk is actually being recorded for a wider audience. And so I'll review a lot of things that you learned in undergraduate. The wall is actually pretty interesting. There are several of them. There's the power wall, there's the clock rate wall, and there's a third wall that I think is actually pretty important, which many people don't think about too much, which is the complexity wall. These walls are going to force us to build future systems in new ways. We've before always been able to rely on higher performance for single-threaded programs. And I'm sorry, but that era is now over. We have to do something different. Otherwise, we will not be able to continue giving computers the ability to affect our lives in the way they have in the last half-century. So, in designing these new systems, we should actually examine some of the decisions made in the past. And we may, choices that we made may actually be less relevant today given the new technological landscape in which we find ourselves. Computer science is actually a very forgetful discipline, probably more so than any of the other major sciences. And I think I understand why that is. It's because the underlying technologies have changed so rapidly that we've had to continue innovating at a very frequent rate in order to employ them. And we tend to forget that a lot of things that happened more than 10 years ago did happen, and some of them were fairly good ideas. There was a speaker who spoke at this conference yesterday and described 1994 as ancient history. So I suppose by those standards that I am prehistoric. But there are others that agree with my position on this. I was delighted to hear a talk given by Bill Daly earlier today, a keynote address, in which he talked about some of these issues. And I was also delighted to discover that this month's issue of the Communications of the ACM carried an article by Peter Denning and Jack Dennis, which spoke to some of the same issues. So let's look at this progress that we have had over the last 40 years and use it to try to understand what's going on and what the future is going to look like. This is a chart that I use sometimes to compare the characteristics of the 1972 Alto with my home PC today in 2010. I don't have the costs involved, but I probably should. The Alto cost $12,000 at a time when $12,000 was actually a lot of money. I bought my home PC a few weeks ago by going down to a local computer store and paying the princely sum of $900. And what we got for that money in 1972 and 2010 were as follows: a CPU with a clock rate of 6 megahertz versus 4 CPUs with a clock rate of 2.8 gigahertz. That's a factor of 1900 in speed. The memory size for the Alto was 128 kilobytes. That is an unimaginably small amount of memory, approximately the size of a level 1 cache or a small level 2 cache in one of today's cores. My home PC today has 6 gigabytes of memory, and that's a factor of 48,000. I've been a little surprised over the years that I keep having to have more memory, because the Alto would do a lot in 128 kilobytes. What happened? And I'll talk a little about what happened. Part of it was that software does more, and part of it was that we just helped. There's another law, actually. I'm going to talk about a couple of laws today, but there's another law which was put forth by Nathan Myhrvold, who used to be the CTO of Microsoft. He said, software is like a gas. It expands to fill the available space. So, memory access time. Now, this one's a little bit tricky because the Alto had an 850 nanosecond access time, and my home PC has a 50 nanosecond access time. That's only a factor of 17. So, we see the memory wall right here. The CPU got a lot faster, the memory didn't. What do we do to fix that problem? And architects over the decades have risen to the occasion and provided various solutions, and we'll look at some of those solutions. And ask the question, would we make the same choices today? And I don't actually know the answer to that question, but I think it's worth asking the question. So the network, the original Ethernet was 3 megabits per second, and now it's a gigabit, or if you're operating in a more limited environment, perhaps 10 or 100 gigabits soon. That's only a factor of 300, but it seems to be enough for a while. The disk capacity is the interesting one. 2.5 megabytes for the Alto, 700 gigabytes for my home PC, a factor of 280,000. So there are a lot of exponential drivers going around in computing, and we've kind of gotten used to exponential growth. The largest one is, of course, rotating magnetic storage. Today, we can put every single bit, digital bit, of every piece of information that you receive, all the videos, all the television, all the things that you read, over the course of your lifetime, on a few disks. And there are actually a few somewhat odd people, like my colleague Gordon Bell, who are actually doing that. Glass fibers is something that we don't think about very much, but a few years ago, Rob Pike pointed out to me that the progress in our ability to make clear glass into fiber optic cables and then to multiplex multiple wavelengths onto those cables has revolutionized both computing and communication. Today, of course, there are no 2 points on Earth that need to be more than 50 milliseconds apart. And we see this when we pick up and make an international phone call, which used to go by satellite, and then one half of it went by satellite, and now the satellites are used to broadcast soccer games. The telephone calls all go by fiber, and calling from my home in Palo Alto to anywhere in the world is as if it was a local call. The most well-known driver for technology is the law that talks about semiconductor progress. Now, this is, of course, not a law, And it was just a sort of an observation made by Gordon Moore in 1965, and a lot of people didn't get it. They didn't quite understand what he said. He didn't say that chips would be faster, which they have been, or that they would get very hot and dissipate a lot of power, which they do, but just that the number of transistors that he could put on a silicon die of a given size would about double every 18 to 24 months, and he said, for the foreseeable future. The foreseeable future has now been 50 years. A little more, actually. So it's actually instructive to look at one of the other laws that we have in computer architecture in order to understand the nature of the walls. Okay, we could have predicted the walls quite easily, and some people did. And it all depends on this one equation at the top of the page, and I swear to you this was the only equation in the talk. The power is the capacitive load on a circuit multiplied by the square of the voltage multiplied by the frequency. And this relates power and capacitive loading and the operating voltage and frequency, and that's really all you need to understand the wall. And conventional scaling, which has worked for many, many years, says that if we scale the capacitance and the voltage down by a factor of k, then the new power is C over k times V over k squared times F equals the original power divided by k cubed. Now that's pretty good. K is the feature size, of course. 90 nanometers to 45 nanometer transition is a k equal 2. So the new chip is 1 over k squared in size and 1 over k cubed, the power at the same frequency. But of course, you don't do that. What you do is you use this wonderful opportunity to scale up the frequency by a factor of k as well. And what happens if you do that is the power per unit area is unchanged. And that's an interesting observation because usually it would be the case that people who were content with the present speeds would say, well, I just prefer to have a chip that is 1 over k squared is expensive, by the way, because since, of course, wafer processing is pretty much constant in price, and the area, the number of chips you get is proportional to the area of the die. But that's not exactly what people have done. And the major semiconductor vendors have used scaling in different ways. So you might think that since the power does go inversely as the die area, the new chips would be cheaper. And there's only one area that I know of where that actually works, and that is in video game consoles. When a manufacturer of a video game console makes a new console, they go out and they pay very large amounts of money to build the very first version of the console in the fastest available technology that money can buy. And these consoles have a life cycle of about 5 years. And over that period of time, since the video game players do not want the game to play any differently, the manufacturer gets to do something. He's losing money at the beginning of the life cycle, and then the first factor of 2 comes along in size, and the new box has chips that are 1/8 as expensive. And if you do that again, by the end of the 5-year period, you're making money. And all throughout the process, the games themselves have been subsidizing the console. So if you do it right, and you pick your technologies correctly, and it works for a period of 5 years, you clean up. We missed that the first time, the first cycle of the Xbox, and we made it on the second cycle. And I think Microsoft is now the major player in console games. So, as I said, the manufacturers use scaling in 2 different ways. The people who make RAMs, that is where we saw that factor of 28,000, use scaling to improve the density. So they use slightly lower voltages, somewhat higher frequencies, but not a lot, and somewhat higher power, but not a lot. Memories do not require complicated heat removal. They will cool themselves if you just waft air over the chip. But they got a lot more bits. And CPU manufacturers took a different path. They used scaling to allow higher clock rates. And in addition, they used more complex designs in order to improve the speed of the CPU. And the result was that the CPUs got very hot, which is the power wall, and memories got bigger, but not much faster. That's the memory wall that we saw in the chart on slide 2 or 1. So future trends, rather than seeing a single very fast CPU, which was in the technology, the roadmap for semiconductor technology, predicting a few years ago that today's clock rates would be on the order of 10 gigahertz. They're not. They're on the order of 2.5 gigahertz or 3. Rather than seeing these ultra-fast beasts, what we'll see is more of them. And the ones that we do see on the chips will be simpler, or perhaps some other things might happen. We might wind up seeing chips that were heterogeneous and had different kinds of processing on the same die in order to even further optimize the performance that you get for a given amount of energy. But of course, we worry a lot about energy today because we're running out of it. And for companies like us who build large data centers, the problem is actually quite severe. So we spend a lot of attention on it. So given this understanding about the scale drivers for performance and energy and cost in computing, we can go back to those examples I talked about that say why it's a good idea to look at the past in order to figure out what to do in the future. So the first example that I use is virtual memory. Virtual memory was introduced in the early 60s in the Manchester Atlas machine. An Atlas had a 16 kiloword core memory and a 1 megaword magnetic drum memory. Just to calibrate me, how many people in the audience have ever programmed a machine that uses a magnetic drum for its main memory? 1, 2, 3. That's it. Okay. Drum memory, RIP. So virtual memory is actually a very simple and very clever idea thought up by Tom Kilburn. The simple idea was to make the core memory appear to be as large as the drum, and a very simple thing was done. They divided the core memory into 32 512-word pages, and they used an associative memory, which we now call a TLB, to map virtual drum addresses into real core addresses. And they also had an operating system that used what they called a learning program to decide which pages to transfer back to the disk so that there would always be a free page to handle a miss when none of the associative comparisons on the page address register succeeded. Well, it's a fine and simple idea, and it's actually used in most computers today, except for supercomputers and embedded systems, very small embedded systems. Embedded systems don't need virtual memory because they have plenty of real memory, and the supercomputer guys think the same way about it. And in fact, Seymour Cray is rumored to have quipped, real programs need real memory. He said an awful lot of interesting things, like parity is for farmers. That is, farm subsidies, parity. So let's talk a little bit more about virtual memory. Over the years, the speed of systems increased, as did their size, and we got problems. The memory sizes grew much faster than the page size, and so we got larger tables. And as was pointed out today at this conference by one of the speakers, associative memories are expensive to build and usually very slow. So what we did was use caches instead of fully associative memories. So we cached the page tables. And when we got to multi-programming, where there were several independent processes running on a single machine, then we had one of these tables per process, and that just made things worse. So we did what architects always do. We innovated, and we tried a lot of approaches: paged tables, segmented addresses, paged segments, and those things have worked pretty well for us, but there's still a modest amount of overhead in a virtual memory system. And having one sometimes has unexpected consequences in other areas. A few years ago, I was involved in a project to build a tablet PC. And this is a portable device that runs on batteries, and we were quite worried, this was 1999, about the energy consumption of this PC. And so we wanted it to be able to go into, when it was not being used, to go into its so-called standby state very efficiently and then come back out very quickly. And that worked fine, and the tablet would go into its standby state. But when it came out of the standby state, something fairly mysterious happened. It turned out that you had to spin the disk up before the system started to come out of standby. And after poking around, we discovered what happened. It turns out that in the Windows system, the device drivers are not written by Microsoft. They're written by the hardware vendors. And so the people who wrote the drivers for some of the I/O devices that we had used in this tablet PC didn't quite do it right. It turns out that when Windows is ready to go into one of these low power states, it sends interprocessor messages to all of the I/O drivers saying, I'm about to turn you off, and please page in anything that you need in order to reinitialize your hardware when power returns. And when all of that is said and done, Windows causes the system to put the dynamic RAM into what's called self-refresh mode, which actually draws very little power, and then power down the disk, the CPU, the display, and anything else that there is, except for a very small core of very low power logic that waits for you to push the button that says turn back on. But what was actually happening when we sent those messages to those drivers is they were saying, okay, I've done everything you asked, but in actual fact, they hadn't done a damn thing. And the result was that when you push the button, the very first thing that happened was one of these drivers got a page fault, and you had to spin up the disk. We sorted that out eventually, and today, laptops do go in and out of standby correctly, but what I told my laptop-toting friends at that time was, if you really want to stop these delays on coming out of standby, just disable paging. And they looked at me like I was from Mars and said, that'll never work. And I said, just try it. And what happens is, the problem goes away. Except after a few days of operation, the system pops up of a message that says, I'm getting low on virtual memory. At that time, you just reboot. And you do it at a controlled time, and everything is fine. This, of course, wouldn't work if you had a very complex application. It required a lot of memory all the time because it would run out too fast. But for many things that people use laptops for, it works just fine. Of course, those days are behind us. And these things now work. So VM still solves a few problems today. One is protection. Protection is something that was added on top of virtual memory a little bit later. And the idea is you could set bits in the page tables that say what a given program or operating system mode is allowed to do to this memory, and only the operating system can modify those bits. Protection will be a problem as long as we continue to program in archaic languages that allow users to express pointers, like, say, C or C++. I don't actually program very much in these languages except unless I absolutely have to, because I make too many mistakes. And the compiler can't find them, and I spend a lot of time debugging, which I don't like to do. So I prefer to write in a language that is type safe and has a garbage collector. The problem of relocation, which means that you can build an image for a fixed location, starting at a fixed location, typically 0, and actually put it anywhere in memory, is another problem that VM solves. But segments are actually quite a bit simpler, and maybe we ought to consider a simpler system that use segments. Fragmentation is also a problem. Occasionally your program will ask for an array that's larger than any contiguous region that currently exists in real memory. But if we're using one of these non-archaic programming systems, then it will likely have a compacting garbage collector which maximizes the amount of storage available for any request at all times, and you'll be quite happy. So the bottom line on VM is that it was invented at a time of scarcity. The size of real memory today is really no longer a problem for the systems we build. So is it still a good idea? I don't know, but I think it's worth asking the question. Well, that's interesting. Okay, example 2 is coherent shared memory. Until the 70s, of course, coherence wasn't really an issue. It was when we got caches that this changed. Originally, when you had a unit processor, the only coherence issue was between the processor and the input-output devices. And even when we got the early multiprocessors, bus-based snooping protocols were adequate, and they were actually quite simple. When we started to build larger scale multiprocessors, however, in the early 80s, things changed, and the protocols actually got quite a bit more complex because buses no longer worked. We had to have point-to-point links, and so the protocols were more complex, and as the complexity went up, manufacturers turned more and more to formal methods. This is actually one of the earliest uses of formal methods in anger, that is, to solve real problems as opposed to try to, for instance, prove programs correct, which people have been doing for quite a while, to ensure correctness. And in fact, today, I believe it is the case that the largest user of model checking on the planet is Intel, and they use it to verify the correctness of any changes that they make to their, by now, extremely complex coherence protocols. I was actually working for a while on the Xbox, and I had a student who, an intern, who had used model checking quite effectively on several things, and so he did an internship, and we looked together at the coherence protocol in the Xbox 360, which is actually a pretty simple protocol. And we didn't quite get the model complete over the 12 weeks of his internship, but in the course of setting it up, we found a bug. And it turned out to be a fairly subtle coherence bug. And in fact, after a few weeks, IBM actually fessed up and said, you know, that was a bug. And our suites wouldn't have found it. And 4 months, or 4 days, 4 hours after you got the chips, they would have deadlocked. I really tried to send that kid back to school in a Mercedes, but I was unable to get the money. So originally, the early 80s were actually another interesting time in computing. They were approximately the last time where a small group of people could actually design and build a new computer architecture, and if they wanted to, build it at scale, somewhat small scale, and use it in their daily work. That was what we done at PARC, that's what we did with Firefly, and that was actually the last time we could do it, because the complexity needed to build a system that was in any way competitive to what you could actually reach out and buy was just impossibly expensive. And chip fabrication was really turning into a big deal, and of course today those problems have been exacerbated to the point that there are no longer a large number of fabs on the planet because they simply cost too much. So if we got rid of coherent memory, what might we replace it with? Well, one possibility is message passing. And I've puzzled about this because we've known since about 1977 in a paper by Lauer and Needham that message passing and shared memory are actually duals of one another. Under appropriate interpretation of what you use them for, they all do the same thing. You can do anything with one, you can do with the other, and vice versa. But actually, messages are quite a bit simpler than these complicated coherence protocols. So why did we go down the path of building shared memory systems? And I thought about this for a while, and I concluded there are a couple of possibilities, and there may be more. I would be delighted to hear of them if there are. Possibility one was that programming is easier. That is to say, if you build a message system and you get it wrong, and then your program doesn't do anything, or it deadlocks, or something like that. If you have a shared memory program and you try to convert the original sequential program into something that runs in parallel or runs concurrently, you can debug it into existence, and it may appear to work, but it may have subtle timing bugs and things like that. And so my own view is I would rather have a correct system than an easy-to-build system, but a lot of people disagree with me. Possibility two is that we lucked out and we could make it work adequately at small scale, and we didn't quite foresee the complexity that larger scale would introduce. So you might ask whether we'd make the same choice today. Again, this is one of these things that I don't know, but I think it's worth asking the question. Example number 3, threads and locks. And we have a little quote from Edgar Dijkstra here. Edgar, a little like Seymour, would throw out these things as absolute fact, and well, that was okay. Edgar was a very smart guy. He says, "I am convinced more than ever that this type of work is very difficult, and that the effort to do it with other than the best people is doomed to either failure or moderate success at enormous cost." And the interesting thing is that what Dijkstra was talking about was the problem of doing concurrent programming on a multi-programmed uniprocessor, not the problem we have today. But what we do find is that lock-based programming is still very hard. Coarse-grained locking is very simple, easy to make work, but it's very inefficient. Fine-grained locking is very difficult to reason about and very difficult to get right. Bugs are frequently non-deterministic Heisenberg bugs. You can't go back and find them. And I used to think that this was a problem of education, and we should provide this sort of best practice guidance by some of Dijkstra's best people so that we can have a lot of ordinary programmers writing concurrent programs. But I no longer believe that. The fundamental problem here is that lock-based abstractions do not compose. And what that means is if you plan on building a higher level abstraction based on two or more lower level abstractions, you had better understand the locking discipline of the lower abstractions, and that destroys information hiding, which is the thing that we use to structure our programs and makes them understandable. So In the era of mini-core systems, we can't just write programs with the best people, because we're going to have to write a lot of code, because yeah, it's hard to change code, but if we don't do it, we're doomed. So, are there alternatives to locks that might work? Well, one possibility is transactional memory. So, this technique borrows from the database community, which has been doing transactions for years, and they have 4 properties. Transactions are atomic, that is, everything done within a transaction either commits as an atomic action or aborts if something goes wrong. They're isolated, that is, what goes on in one transaction can't cause any problems in another. They're not necessarily durable. There have been a lot of designs. I have a friend who has, Tim Harris, who's written recently the 2nd edition of a book about transactional memory. And when asked to describe at a workshop earlier this year, kind of what the major message of the transactional papers that he reviewed in this book were, he said, well, I can't quite figure it out because there are 500 of them. So there have been about 500 papers written over roughly the last 10 years about transactional memories. And they have problems of their own. They're definitely not a panacea because some of the problems are really pathologies. You can't do I/O in a transaction. You've got to figure out how to do something else because, as Simon Peyton-Jones once pointed out, you can't unfire the missiles. There are arguments similar to the coarse-grained, fine-grained locking around transactions. And one of the things that I have the most trouble with about transactions are that transactions are a form of speculation. And I'm actually quite nervous about speculation because what speculation is you do a lot of work on the hope that you'll get the right answer, but you have to throw that work away if you don't, and you waste energy and processor cycles in doing that discard. So if you build a system that uses transactions and one of the transactions aborts frequently, then you're wasting a lot of energy, and this is bad in this new world. But I think there's a worse problem. It's an engineering problem, actually. We don't have any experience with transactions used in a memory system. We need some actual implementation. We need better benchmarks. We have about 4 benchmarks for transactions that everyone uses. It's a little like everyone uses SPEC in the architecture community. The subset of the architecture community that works in the area of transactional memory uses about 4 benchmarks. We need to build some real transactional systems just to see if we can do it. And there's a lot of chicken or eggness here. Why should we build a processor capable of doing transactional memory fairly efficiently if we don't know whether it's actually going to be useful? Another contender for an alternative to threads and locks is pure message passing, but I think that's probably beyond the pale. So, yeah, the final, no, it's not the final example. Example 4 is complex CPUs. This is the complexity wall. And for this I need a timeline, which I'm happy to provide. In the 50s and 60s, we were in the golden age of experimentation. A lot of people experimented with variations in computer architecture. We built decimal CPUs, things that process strings, single language CPUs for a wide variety of languages, some of which were very nice. I think that the B5000, for instance, is one of the most elegant machines ever designed. It only does one thing well, which is run out-all programs. But if you want to run out-all, it's an elegant, if not terribly fast, way to do it. We even had stack machines, some of which I built. Stack machines are great. They have enormous code density. They have a few problems in performance. The 70s and 80s were an interesting time because two major things happened. A lot of these architectures just vanished. And these times were a period of consolidation and what I call religious warfare. There were two major surviving architectural classes. The first was the RISC, and that's reduced instruction set computing, of course, and that was typified by work done at IBM and Stanford and Berkeley. And that did battle with the CISC architecture as typified by the x86, which was still an evolutionary architecture from Intel. And a lot of people wrote a lot of papers about which one is better than which. And what actually happened was those things eventually died out because the proponents in the two different camps discovered that the other guys actually had some pretty good ideas, so they started taking ideas from one another, and pretty soon you could barely tell the difference between a RISC and a CISC. And so this kind of went away. The 90s was a more interesting period. The 90s was a period of essentially elaboration and the quest for instruction-level parallelism. What architects did during the 90s was primarily, and this is extended through today, and we've heard some papers at this conference that exemplify this point precisely. Basically, the original, very simple ideas in both camps, both the RISC and the CISC camps, were heavily sort of elaborated in order to get higher performance. We went to multi-level cache hierarchies. We went to multi-threading of various kinds. We certainly went for longer pipelines so that we could run the clock rate up. And we did a lot of speculative execution everywhere. And if you recall, speculative execution is not a good thing if your speculation fails, because you waste work and you waste energy. We made a lot of sort of incremental advances in performance. A good paper would have, it'd be something that went roughly like, I modified the so-and-so architecture, typically the RISC architecture, because that was what the academic community could work with, in the following way, and I ran the spec benchmarks on a simulated version of this new architecture, and I got between -3 and 7% improvement over all the spec benchmarks. So people were trying to use complexity to dig the last bit of instructional parallelism out of what were actually sequential programs that had originally been written as sequential programs. And the fundamental problem they discovered is that there really isn't a lot of ILP available in such programs. So a lot of this additional logic and additional complexity and additional power and additional energy was not very well spent, in my opinion. But if we look today, there are some possible new directions for CPUs. The one that I find most interesting, because it parallels to some extent my view about what architecture is going to look like, is, or should look like, let's put it that way, is the Intel single chip cloud computer. This is a pretty interesting device. It has lots of simple cores. 48 at the moment, and what I have been told is that scaling to 100 is perfectly feasible. These are older cores. They're in-order execution cores, very short pipelines. They're P54C cores, which are about 10 years old, I believe, maybe more. There's no coherence in this system at all. If you want it, you figure out how to do it, and you provide it. There are actually small caches, but the major resource that the processor has at its demand is a small local memory. Maybe a little bit too small, but that could be fixed. And it has a very highly efficient inter-core network. Another trend that we see is lower power cores. Remember that k squared, k cubed dilemma? Well, a lot of people are recognizing that for a lot of the work that we do in the world, today's computers are simply fast enough. And what they would rather have is better use of energy and lower price. And so the manufacturers are actually catering to this demand in the form of things like the Atom chip, which is a very nice chip, actually. It doesn't dissipate a lot of power, but after all, if I'm sitting on a plane editing a PowerPoint presentation or reading a book or watching a movie, it's more important to me that I can make it across the Atlantic on one battery charge, and with my new laptop I can. It has a battery lifetime of 13 hours. So this is another possibility in the way we could go, particularly on a desktop. So the final example for classical architecture that I think we ought to really look at is the idea of interrupts. Do we really need hardware interrupts? We heard Bill Downey today say something that I agree with in spades. Interrupts are really clunky. They usually were added to systems that after the main part of the architecture was defined, deciding in the many-core world where to deliver an interrupt is actually a pretty difficult problem, because the thread that launched the thing that caused the interrupt to occur is liable to have moved by the time the interrupt actually happens. So it seems like in a world where there are a large number of cores, interrupts have a much less understandable value. And they definitely increase the hardware complexity a lot. And for a long time, they were the major source of errors in the system. If you plugged the wrong kind of I/O devices into the connectors of your PC, the interrupt system would screw the machine over, and it wouldn't work right. And it was very difficult to detect that. And we know that it's possible to build systems without interrupts because people have done it, and they've been quite successful at it. Earliest example that I know of is the BBN Pluribus, which was the ARPANET IMP for the second version. This was a very nice system that had essentially a non-preemptive multitasking system implemented on top of a machine without interrupts. So to explore some of these ideas, in my laboratory, we have implemented a new machine called Beehive. And Beehive is implemented on a single FPGA development board, one of the ones that was described by one of the speakers earlier today. I built this because for the last few years I've been working with this RAMP consortium, the research accelerator for multiple processors, and I realized, so we did several things. We had actually a different mechanism for that. The machine is called B3. In this conference there's been a lot of reported work on using the predecessor B2 machine, and B3s are now coming into play. We also caused a startup to appear to actually maintain and support the B3, and they're thriving. So this isn't something that we normally do, but as a model for interaction between academia and industry, I think it's worked pretty well. But after doing that, I looked around and I said, well, the research, Research Accelerator, or Research Acceleration for Multiple Processors Consortium talks about being an organization to do multi-core design. They don't have one. And the problem is that the cores that you can actually get, that you can implement on an FPGA, are either opaque, that is, you don't get the source code, so you can't fiddle with it. They are expensive, you have to pay for them, or they're too large. So you can only get one or two of them on something the size of, say, the V3, or more to the point, this development board that people can actually buy for $750. So I said, well, I know how to design computers, I'll just build one. And I did. And it's been a pretty interesting idea. We built this thing by writing a big Verilog program of about 6,000 lines of code. And we were interested in a system that we could actually give away that could be used in schools to teach architecture to students in a way that they would like to learn it. I've been actually disturbed at the large number of people within my own company who actually don't know how a computer works. They believe that it all stops at the C compiler. So we've done this machine, and we've done a tool chain for it, consisting of compilers for the Microsoft managed languages, C# and its friends, and a C compiler. Yes, we still program in C, I'm sorry to say. And assembler, simulator, things like that. We license this to anybody for research use, and our first students are actually MIT students. This thing was used successfully in January at MIT to teach an AP course, which is one of these inter-semester courses that they teach that last for a week or two. And the students, if they're optional, there's no grading. And 14 students applied, and they loved it. They were able to do things that they had never been able to do before. And MIT is now using this stuff to do a full semester course in the fall. So there's actually a precedent for this, which is the NetFPGA thing done at Stanford. This effort, which was led by Nick McEwen, has actually changed the way universities teach networking. And it's roughly the same thing. They have a board and some courseware, and they just give it away, and those universities buy the boards. They're a little more, but they've sold about 1,300 of them to date. If we could have a success rate like that in architecture, I would be a happy man. So the characteristics of this machine, it provides 13 very simple RISCs. They're completely homegrown. They kind of have to be, because if we're going to give it away, we don't want somebody to come along and say, you're using our architecture and violating 17 of our patents, please pay up. And so we did it in the entire thing from scratch. 1 gigabit Ethernet controller, a display controller, 2 gigabytes of shared DRAM, non-coherent memory, and hardware-supported message passing, just to see if we can make that work, and hardware-supported semaphores, binary semaphores. So this is not intended to be competitive with real systems, but basically to be a lot more malleable and faster than simulators by a lot. So 13 100 megahertz cores is not a shabby machine, even by the standards of 10 years ago. And of course, it is big enough and fast enough that you can run complete OSs. And in fact, we have no ambition to run Linux or to run Windows on this thing, but a new operating system that has been developed in our Cambridge lab in collaboration with the ETH in Zurich, called Barrelfish, is a port target for it, and that's happening right now. So here's what a Beehive core looks like. You probably have not seen a picture like this for 25 or 30 years. It's a very simple, in-order, 3-stage pipeline. It has 32 registers, 32-bit registers, 2 read ports and a write port, and an instruction cache and a data cache. Data cache not shown. They're both 4 kilobytes, so they have, it's not very good hit rate, but they're fast enough, because in fact, as we'll see in a moment, the speed ratios in an FPGA are quite different than they are in a real system. When you do work in this kind of an arena, you have to be constantly aware of what you would have to do to your design in order to build it in real silicon. It's not the same, but you do have to optimize for the medium in order to get it to work at all. There is one kind of weird thing about this machine. It's a decoupled architecture. You note that there are 3 queues, the address queue, the write queue, and the read queue. Decoupling the idea of issuing an address and taking the data is a kind of an old idea. When I heard about it, it was from Bill Wolf, who had put it in a machine that he was designing when he was building high-performance Ada compilers in 1980. And he wanted an architecture that he could use as an output for the Ada compiler. And in fact, his machine didn't have caches. And so he liked this decoupled architecture because he could write compilers that could hoist the load way above the use and hide a lot of latency as a result. And I talked to him about it, and I said, I think this is an extremely clever idea. Bill, mind if I steal it? And he said, no, go right ahead. So one of the problems about an FPGA is if you have a lot of cores, you generally can't hook them up to the memory, because in an FPGA, the critical resource is actually long wires. There are some other resources that you run up against, but that's the first one. So in order to do that, overcome that limitation, we used a token ring interface that you see here. Basically, I liken this to a train where an engine leaves the station, that is the right-hand side of that memmux module, that says, here's a token, and anybody who wants to make a memory reference can add an address slot, or a write data slot, or a message slot, or a lock slot. And those slots travel around the ring, the train getting longer and longer until they get back to the main station, at which point they're peeled off and sent to the DDR controller, which is much, much faster than the ring itself. The ring can provide a total of 800 megabytes a second of bandwidth, and the read data is actually returned on a separate pipeline bus, so that's another 800 megabytes a second. But that's still like a quarter of the speed of the memory. So our display controller can actually overwhelm the ring so we don't use it at all. We have a side path into the DDR controller, but the DDR controller is an old design. It's worked for like a year. It's solid as a rock. So the reason we did it this way is we didn't want to spend a lot of time floor planning this design. We just pour this thing at the Xilinx tools and let it rip. The 13-core version takes about an hour and a half to build, which is tedious if you're making a one-line change to the Verilog. But when we do that, we turn the number of cores down to 5, and it's pretty reasonable. So my last, we're doing on time, yeah, that's okay. My last example is not a computer architecture example, it's a packet switch networks example. I was surprised today that the ISCA community does not think of networking as part of their purview. They are microarchitects. Networks are something else. And I actually don't believe that's true, because there are 2 areas where you kind of can't tease them apart. One is, inside a chip, is a network different, or is it part of the architecture of the chip? And I would argue the latter. You won't do well at building a many-core chip if you do not pay attention to the communication. And as I said before, although the trade-offs in building real chips are different, you're going to wind up doing something like that ring, probably meshes or whatever. That's what the single-chip cloud does. In order to get around some of the communication limits, just shipping data around is expensive. So I observed that today's large data centers provide us with a wonderful opportunity to re-examine local area networking. Data centers are not the internet, and we shouldn't think of them as the internet. The differences are shown. They have a known topology, You know, that in principle, the name of every machine in your data center because you paid for it. They have very small diameter, that is physical diameter, and what that means is that the interconnections are relatively low latency. There are fewer end nodes, maybe tens of thousands rather than hundreds of millions. And the interswitch links in such a network are quite fast, 10 gigabits per second today, and probably by the end of next week, 40 gigabits per second. And then a few years later, 100 gigabits. So bandwidth is no longer quite the problem that it used to be. The other thing is that the traffic patterns inside a network are inside a data center are quite different than they are in the internet. And we can exploit that. So the question that I ask is, why should we use packet switching? Now, to be fair, we're not going to get rid of packet switching in the internet anytime soon. It works reasonably well, although not as nicely as some of us would like, but the cost of replacement would be much too large. But that's not true in a data center. When we get set up to build one, we're building ab initio, and making a change like that would actually not be very bad. So why did we do packet switching originally? Well, we had a medium that was underutilized by an individual station or an individual communicating pair of stations, and we found that 3 megabits a second was fast enough, thank you, to support a fairly large population of stations. And so it was cheaper to do it that way. Retransmission on packet loss worked fine as a congestion detection methodology because of the small network size. And in the original network, we made the same mistake, right? Never supplying enough address bits. So we actually, in the original Ethernet, had an 8-bit station identifier. We ran through that one fairly rapidly. 32 bits was better, but they made the same mistake. Probably should have just used the MAC address. We had a 48-bit MAC by that time, and that probably would have lasted. But instead, we had to go to 128 because you always have to double, causing a lot of trouble. So when Ethernet evolved, and of course Ethernet today is nothing like the original Ethernet, it's just the name hasn't changed, and some of the parameters are the same, like 1500 bytes is an enshrined number, but everything else is different. What we found was that point-to-point links with which these things were implemented rarely actually make errors, but the switches and the routers and the buffer still need these huge buffers, because if the traffic pattern happens to be such that a lot of people are directing traffic to a single node, then the buffers fill up and the latency suffers, and if you're not careful, you get this thing called the NCAS problem, where the network throughput around that switch and end node just simply collapses. The routing decisions in a packet switch network have to be made at every switch. And they're complicated because you have to look at a lot of fields in the packet header to decide where to send the packet. So as switch and router complexity grew, reliability actually suffered. These things have a lot of software, and it's software that is just as old as our software and maintained in similar ways, and it breaks in similar ways. So unfortunately, as network speeds go up, a lot of these mechanisms like window-based congestion control work much less well, because the fundamental problem with TCP is that you hear about a problem after the damage is already done, and you've already dumped the packet on the floor. And if the links are long, then the windows will go very small, very fast, and spend a long time coming back up to their original size. So I'm wondering, should we revisit circuit switching? Now, circuit switching is actually used in the internet. It's used in the backbone. In the form of ATM, it's used to carry traffic between the large ISPs that actually provide the backbone And nobody kind of knows that it's there, although some people will admit it. What they do is use admission control rather than congestion control to avoid data loss, except for the rare cases when an error actually occurs. So you just don't, it's like the phone network. You pick up the phone, you don't get a dial tone if you can't get a connection, and you might get a busy signal when you do. It works exactly the same way. You determine the routing through the network at call setup, and you don't have to change it thereafter until you're finished with that, what we would in the internet parlance call flow. And in the data centers, the flows are sometimes very, very long. You know, you're sending hundreds of megabytes between nodes. And so the flows exist for a long time, and the schedule, this call setup, is amortized quite easily over such large flows. The key to making all this work is to make the call setup time much, much less than the transmission time. Now, in a data center, for all but the tiniest transmissions, this can work because the links are short, and so the latency through the network is actually quite low. So it's likely that you can set up and tear down connections in such a network at a high enough rate that we could do it. And the advantage of doing it is that the switches are remarkably less complicated. They have schedules in them. They look actually like a telephone company time slot interchanger from the 1950s. And as a result, these networks require almost no buffering. If you buy a large packet switch today, you're buying tens of megabytes of buffering on that chip and thousands of tiny packet processors, or hundreds, to process the packets to decide where to route the network. An arrangement like this would actually be much simpler. And so we're studying such a thing in my laboratory. The interesting thing about it is we actually believe that you can implement this with FPGAs. It's not clear that you would want to do that in large volumes, but if you wanted to build one or two, you might be able to make it work with today's modern FPGAs. And here's a possible arrangement. Basically, this is designed for a data center that uses shipping containers. So in the entire center, there are 64 containers, each of which have 2 rows of racks. Each rack has 40 1U slots for computers or other things. And that 1U has a lower bandwidth, probably not only 1 gigabit, you can think, but probably more like 2.5 gigabit, uplink to a level 0 switch in the middle of the rack. And those aggregate the 20 switches into 2 10 gigabit per second links, which run to the 2 level 1 routers, switches that is, at the top, at the edges of the containers. And each router, each level 1 switch has 64 optical cables going off, and they connect, each one of them connects to each of the other 63 containers in the data center, plus 1 remaining link for the network operations center. And that's carried along twice so that these level 1 switches can fail. And when they do, you lose half the bandwidth of that container, but you don't lose the connectivity. Now, what a level 0 switch failure does is lose you 20 CPUs, and that's just fine. Just mark them dead. So you don't have to enter these containers if you don't want to. You can just let the contents rot. And then when they do, or they've depreciated, or new models have come out, you just send them back to the manufacturer across the water and have them refurbished according to your new druthers. So this depends a little bit, as I said, on making this call setup work well. And that's done by these things called route controllers attached to the level 1 switches. They're actually part of the level 1 switch, but I won't go into detail. This might actually work, and if it did, it would save us a lot of money and a lot of reliability, and our customers would be happier because one of the things we've learned about these large switches is that they do fail. And it takes a long time to get them fixed because we don't actually know what's inside them. So, whoops, wrong way. So let me share some final thoughts with you, and then we can go off and have some wine and this, that, and the other thing. The systems of the 21st century are different, okay? And based on these differences, we should probably rethink some of the design decisions based on the new realities. Because we're going to continue to want to use computers to do new things. I'm sorry, but I couldn't resist a little bit of grand challenge stuff, because I think there are grand challenges, and as architects, we really need to rise to them. And so we need to think a little bit more carefully about what they are. Now, as I said at the beginning of the talk, you weren't going to get very much from me about high-performance computing, because that's not the area in which I've worked a lot. But here are some things that probably aren't high-performance computing applications, but that I would sure like to have, and I think a lot of other people would, and I think they'd pay for it. Why do I have to drive my car? If you look at my car, you will find that it is a bit dinged up in one area, and this is because I'm not a very good driver. If a computer had been driving this car in the parking lot when I was doing it, it wouldn't have the ding. I would like a computer that actually knows about me. My computer does not know me at all. It doesn't know anything about my preferences, except perhaps for my search history or purchasing history, although probably someone out there on the web knows a lot more about that. I'd like to have a computer that could learn my preferences and work with me as a colleague rather than as a slave. Wouldn't that be great? I'd like that. I'd like a computer that could help me educate my grandchildren. I've actually worked on that problem, and it turns out that it's devilish hard. What we were trying to do was teach kids how to read, because reading is actually a fundamental skill. And with the exception of a small blip in the statistics a couple of years ago, reading scores have declined in the United States year over year for about 30 years. And it's really scary, because what we find is that if kids don't become fairly fluent readers by the 4th grade, they are doomed for the rest of their lives. It's just, educators have a name for it. It's called the 4th grade gap. And we tried to figure out ways to help kids overcome the two facts that keep them from reading. Number one is television, and number two is the fact that their parents no longer read to them at night, because everybody has a two-body career. And we tried to use several ideas. We talked to a lot of educators, for instance, and learned how kids actually learn, and tried to build not exactly the kind of edutainment that had been built before, but a game kind of thing. We probably, if we looked at this again, we'd look more at machine learning. But we couldn't quite make it work, so that was a kind of a failed thing, but I'd still like to have it. And I'd also like to have a computer that was actually dedicated to maintaining and enhancing my privacy rather than eroding it, as seems to be the case today. So these are some of the challenges that I think will require that we make fairly substantial changes in the way we design and build our systems today. But actually, no matter what happens in our field, I suspect that computing will continue to be as vibrant and as exciting a field as we move forward as it was in its first half century. And actually, I envy the young people now entering the field, because I'm pretty sure they'll have as productive and exciting a career as I am. Thank you.
Joseph Torellas from Illinois. So you mentioned that there are lots of things that you would like changed. For example, no locks, no threads.
No, I didn't say that at all. What I said was we ought to examine those decisions, not necessarily change them, but we should examine them carefully to decide whether they were really good ideas or whether some other alternative would be better.
Suppose that we want to change them, okay? Suppose that.
Suppose we decided to change them.
Interrupts, cache coherence, and so on.
Mm-hmm.
A lot of these things, they have a chicken and egg problem.
I know.
You don't change because the whole inertia of the system.
I know.
Is there any example in the history of computing where we faced such barriers and we've been able to overcome them by completely changing things?
Actually, we've rewritten our software several times in the course of computing. I think this stuff about legacy preservation is a bit of a red herring. I mean, it's people are unwilling to change, okay, for a lot of reasons. They get into very comfortable ruts. They like to continue to do the things they have done. You know, use the spec benchmarks to examine microarchitectural changes. Use the same simulation environment. Those things are hard to change. And it's a lot of work to do so, and unfortunately, the rewards sometimes don't happen at all, or happen over a lot longer period. We tend to be very short-term in computing these days, just the way businesses tend to be short-term. We're going for the next quarter's performance or the next half's performance. And we really ought to be thinking about long-term survival and long-term progress, I believe.
So the inertia is not any bigger than before.
I'm sorry?
The inertia is not any bigger than in the past, you think? The inertia.
I think it actually is probably a bit bigger because the field's a lot larger. It was a lot easier to change things when there weren't a lot of things and a lot of people working in the field.
David Wood, University of Wisconsin, over here, Chuck.
Gotcha.
Enjoyed your talk. I'm hoping you can give me a little insight on how you picked the examples that you picked. Because, for example, you didn't pick, in some ways, the most fundamental decision that we could reevaluate, the von Neumann computing model, right? And so, was there a rubric that, what was your rubric for picking them, or is it just the ones that seemed right?
Well, I actually could not propose any alternatives that made sense to me to the von Neumann model. There may be alternatives. I mean, actually, we have a group, a fairly secretive group that actually does quantum computing. And that may be a paradigm shift. I'm a little too old and a little too far from physics to really understand quantum mechanics and be able to grok it at the level that I grok the von Neumann architecture. But maybe there are other paradigms as well. But we tried a lot of them. I mean, there was that era of discovery, and a lot of them didn't work. And von Neumann's design survived.
Yeah.
And how did I pick them? Personal preference. As I said, you didn't get to hear anything about HPC because I don't know a lot about it. You have to talk to Burton about that.
Yeah, I have a question.
Okay.
Here. On this side.
Yeah, I'm having trouble actually seeing.
Can you hear?
No.
Can't move out of the lights. Go ahead.
Yeah, Chuck from NEC Labs, Princeton. You talked eloquently about the technology constraints and the impact it has on future computing architectures. And I do agree that technology capabilities do determine what we can build. But I do think that there's an even important driver. It's the emerging applications that eventually determine what type of architectures we build. And once we understand the applications, we build something that the technology allows us. That's been the history.
Well,
in your entire talk, I did not see that aspect at all, the applications aspect. So what are your views on application structure?
Just at the end, those end challenges were applications. And they're big ones, right? They're huge ones. as I say, for many things, we heard a presentation today as part of this conference that says, for many things, the kind of applications that we run today are not really well served by vast arrays of processors. They'll run just fine on something like an Atom. And because they're human-paced, there's not too much point in making them faster. Now, there are some things that we could do in the desktop and laptop space to make the user's life better, and some of those are high-performance things like speech recognition, handwriting recognition, a few things like that. But by and large, you don't need a 256-core multi-core to run PowerPoint. You just don't need it.
Now, you mentioned the 6 changes that we should revisit and rethink. The 6 suggestions that you mentioned that we should revisit. Now, how many of them you think are supported by changes in the applications that we're seeing?
I actually don't think that the kinds of things that I was talking about today would require huge changes in the applications. They make it possible to do different kinds of things, but they don't mandate change. They just give you different, you do a lot of things differently at the low levels of the OS, for instance. But do the applications see anything different? Well, probably not.
My question is a little different. Do you see emerging quirks in the applications that also demand the same type of changes you're mentioning? New emerging applications that are coming out, and you're happy to see them, that they really don't need a coherent memory.
Well,
they really don't need packet switching. They really don't need virtual memory.
I mean, we discussed some of those in a panel today, right? How do we move forward? And one possibility is to think of a world in which we don't have a large homogeneous multi-core machine or mini-core machine. We have a lot of different, somewhat more specialized machines. The trick in building a system like that is going to be to find things where the specialization can be well enough used by a number of the new emerging applications to justify the engineering effort. That's a hard problem. And we may flounder.
Thank you.
Mark, where is Sun Labs Oracle? I'm over here on the left behind the camera.
Gotcha.
Okay. Congratulations on the well-deserved award, and thank you for the very entertaining talk. I have a quick comment and then a request for some advice, I guess.
Okay.
So I and my group have actually had a fair amount of experience working with transactional memory and hardware transactional memory in particular, with a chip built at Sun by a bunch of folks in this room and several others.
Yeah.
You're absolutely right that it's not a panacea. ROC is not a panacea, and transactional memory will never be a panacea. But to me, that does not seem like the criterion to declare defeat. But in listening to Professor Daly's keynote the other day, where he was encouraging us to think about declaring defeat before sinking too much time into something, so that's something that we struggle with. Do we go off and find the next subject to publish 500 papers on in the next decade, or do we persevere where we think there's insight and potential? And I thought maybe you have some wisdom from your career on that.
Well, I actually don't think that the kind of evaluation that we're doing right now is very much work. So, yeah, we wrote 500 papers. And what we found out is that software transactional memory just fundamentally can't be fast enough to be useful in real systems. But that isn't to say that it's a bad idea. The problem with doing the work to justify 500 papers is that it keeps you from writing applications that actually use this stuff. And that's kind of what we need to do now, I think. I believe tiny steps for tiny feet. So we don't understand this stuff. We'll build a reasonably efficient implementation of something that's bounded. We'll write some probably initially toy applications, probably initially benchmarks, to try to understand it. Because it will work in a way that no STM system ever has. It will run at reasonable speed. So we'll maybe be able to learn some things. And maybe we'll find out that it's a bust. But I don't think it's quite time to stop. I do believe in fail fast, which is what Bill was proposing. If you discover that your research isn't panning out, you ought to stop doing it. rather than turning into an advocate for something that's never going to have much impact in the world. I do believe that he's right there. Yeah.
Benjamin Lee, Stanford University. Thanks for your thoughts. Regarding your experiences with FPGAs and prototyping and coming up with actually systems that you've built, do you have any comments on how you might extend the prototypes and the experiences you developed there to systems being deployed in volume? So I think in both cases, both Beehive and the switching example, you said that you built and prototyped the system one way on the FPGA, but if you would actually go and deploy in volume, you would perhaps build it differently. So I don't think you actually closed the gap there, and I was wondering if you had thoughts on.
Well, the idea in doing this is when you're designing something with an FPGA, you're really working at two levels. One is you're working at the abstraction that you're trying to provide to the software. And the other thing is you're trying to make sure that you can actually make the thing work in the FPGA. And that means, as I said, you have to design for the medium. But you have to, at the same time, keep in mind whether you're doing anything that would preclude doing a real implementation. For instance, in our HTM thing, we cannot gang clear the RAM. So there are periods where the system spends 128 cycles clearing a RAM. We just have to factor that in when we look at the results and say, in a real system, that would be one cycle. And you've got to do that quite a bit, but if the system's not enormously complex, you can probably manage that problem.
Here, so this is Ruby Lee from
Right.
Princeton University, and I really liked the examples you chose, because surprisingly enough, almost every one of those examples are better for security than not. So if we had a chance to change the computing paradigm a bit, we might as well include security in it. Now, you do mention in your applications privacy, but there are 2 points you didn't mention, and I'd like to get your opinion on it. One is, of course, today with connectivity, every computer is really literally connected to every other computer, or any computer can be connected to any other computer in the world. And so the problem of confidentiality and integrity and availability is a big issue.
It's a tremendous issue, and I'm sorry, I knew that I would have limited time, and this is not really an area in which I have worked very much, although I have worked a little bit on, secure hardware, like very high-speed implementations of DES encryption many years ago. But it's not an area in which I'm an expert, and I have a lot of friends around me at my lab who are, so I figured that was an aspect I would leave out. As I say, anyone could have picked an equally valid but different set of examples. I just picked things with which I'm most familiar and which are quite accessible in the literature.
But those examples are also good for security. The second thing I want to mention, I want your opinion on is, you said, learn my preferences and be a colleague rather than a slave. But today, there's a lot of thought that viruses spreading at the speed of the internet and malware spreading at that speed might require computers to be autonomous and to perform decisions which are beyond the speed of humans. And
it's certainly true that network computers can do a lot of bad things, and they can do them very rapidly. And that is the problem that we face in security. Certainly, my view of computer as colleague cannot be achieved when somebody can come in and give my electronic colleague a brain transplant. It just won't work. So maybe we'll have to let that one slide for a while, but I know people are really working very diligently on getting security right. And in fact, I don't believe I've ever had a machine that was infected by a virus. No, there was one example when I got a memo. It happened to come from the Microsoft HR department. But by and large, I run my life fairly carefully, and I believe that people who basically expose themselves widely on the net are doing nothing but asking for trouble.
But that may not be the case, but I think for this community, this autonomous computing may be one where this many core thing really might play a part, okay,
Perhaps.
rather than the client platforms.
Right.
Sarita Arve from Illinois. So thanks for the great talk. It's always fun to rethink these types of fundamental decisions, but these decisions often always have implications on the rest of the system. And so to me, it also seems, one of the things that I get from your talk is also that one needs to think about the system as a whole, which we are increasingly doing less of in many communities.
Yeah.
Is that a fair interpretation or no?
That's absolutely fair. I believe that we tend to be very specialized, and we don't tend to, I think I described it earlier today in the panel discussion that we had, of working up and down the stack. We really need people who can work up and down the stack, and rather than specializing in one particular area. You know, I've seen an example, I've seen an example of, this was not any of people that you actually know today, where circuit designers and microarchitects were thrown into a room for 3 months. And the idea was they would either kill one another or they would come out with some really interesting and new circuit technologies. And the latter actually happened, and I got to see some of this. And it was really quite surprising that the two specialty disciplines could communicate well enough to have a substantial impact on what the other was doing. Now, how many levels on the stack you can find a few people to work, I'm not sure. But we ought to work hard for people who can do that.
Hi, I'm Eric Sudlar with what my colleague Mark calls Legacy Oracle. And so my question for you is, you mentioned about virtual memory, and the thing that's really interesting to me about that is if you have an application where the working set of the data processing you want to do exceeds the amount of physical memory you have, you've got two major choices. You can manage that information in a database, or you can manage it with the virtual memory system. And
let me break in just a second. Name 5.
5 applications where the data working set exceeds the physical memory?
The data working set.
The amount of data that you need to process.
Oh, you want to be able to individually address every byte of data on the web, say.
Or every record that was generated by a phone call anywhere in the country over the last, N days or something of that sort.
I'm not
They're
sure.
mostly automatically generated data at this point.
Yeah,
You don't think it's an interesting application space?
we do a lot of data mining. We don't really need it. I mean, we mine everything, and a lot of people mine more. And I don't think we actually need it. And so maybe you ought to go think about how you're solving this problem that you have, because you might find that if you did it slightly differently, you wouldn't need it either.
Well, I can give you an example out of real customers. You take a 100 megabyte XML document, which is not that hard to generate, and you run it through a parser, and it's going to make it get about 100 times bigger, and that's not hard to exceed the amount of physical memory on your home PC today, which you cited as 6 gigabytes earlier. So if you have that application, that's what you want to do, and you want to do a bunch of XML processing, and you want to do tree traversals or things like that, and you have a choice of doing that with virtual memory, or you have a choice of doing that with putting that data in the database.
So for those classes of things, you may decide that getting rid of virtual memory is not a good idea.
Well,
I didn't say that it was.
Actually, no, it turns out that those work better in databases than they do with virtual memory. And my theory is that it's based on the overuse of pointers in applications to use virtual memory. And in the database community, we don't want to let people use pointers.
Yeah.
And those both things you mentioned, I was kind of wondering if that was different 20 years ago. That was a
Well, not for me.
idea.
Not for me. 20 years ago, I detested the use of pointers, and I still do. I mean, I was a man of the future. I stopped using unsafe, untyped languages in about 1977, and I've never gone back. Anybody else? Apparently it's time for a reception. Thank you again.